I find myself in a situation where I need to know some basic math in order to understand neural networks. I am not sure how much I need to learn, but it seems that basic vector and matrix calculus are necessary. As a trained neuroscientist, I'm unsure about the accuracy of my math derivations in my videos. If you notice any errors, please leave a comment. In many cases, neural networks can be viewed as functions with adjustable parameters. These functions take inputs in the form of vectors, matrices, or higher-order tensors and produce outputs. During training, a loss function such as cross-entropy loss is used to quantify the error in the output. The network's parameters are then updated using gradient descent by calculating the gradient of the loss function with respect to the parameters. Understanding the organization of weight and data matrices is crucial when working with neural network packages. It is important to clarify whether each input vector in a data matrix is represented as a row or column. Similarly, it is important to define how the weight matrix is structured. For a layer with n inputs and m outputs, the weight matrix can be represented as a matrix of shape m(n), where each row corresponds to a neuron and each column represents an input connection. Alternatively, the weight matrix can be represented as a matrix of shape n(m), where the roles of rows and columns are switched. Let's explore the weight matrix convention used by TensorFlow. We will create a custom function for matrix multiplication. After importing the necessary libraries, we define a model and display the shapes of the connection weight and bias vector. We then define an input, calculate the output, and compare it with the result obtained using our custom-defined function. Finally, we use NumPy matrix multiplication for the output to ensure consistent results. PyTorch follows a different convention. After defining a layer, we display the shapes of the weight matrix and bias vector. It's important to note that the weight matrix is transposed before computing the output. This highlights the difference in matrix convention between TensorFlow and PyTorch. We will try to follow the following notations. Lowercase bold letters represent vectors. Elements of a vector are denoted by italic lowercase letters with subscripts. Uppercase boldface letters represent matrices. Elements of a matrix are denoted by italic uppercase letters with subscripts. For neural networks, a superscript in square brackets denotes an object associated with the layer. Unfortunately, there are two common conventions in matrix calculus, numerator and denominator. The numerator layout, also called the Jacobian layout, has dimensions equivalent to the numerator, while the denominator layout, also called the gradient layout, has dimensions equivalent to the denominator. It is important to maintain consistency when using these conventions. Here are some definitions in these two conventions. Scalar by vector. Vector by scalar. Vector by vector. Scalar by matrix. Matrix by scalar and matrix differential. The Jacobian matrix is a matrix of first-order partial derivatives that describes how a vector-valued function changes with respect to its input variables. This is an example. The chain rule is effective for scalar equations and index notation but can be problematic when applied to matrix or vector notation, often leading to errors involving transpositions and dimension mismatches. The most reliable method for calculating gradients in matrix or vector notation is through differentials. For vector functions, we have If you are unsure about matrix derivatives involving the chain rule, simplify by breaking everything down into components. Let's consider an example. Applying the chain rule, we get equation. Alternatively, we can express the calculations in terms of components. With 3 elements in Y and 6 elements in W, there are a total of 18 combinations between Y and W. The formula presented here summarizes these combinations. To simplify the concept without using complex math symbols and nested summations, refer to the figures on the right. The final result can be expressed using either indices or matrix and vector notations. If x and y are row vectors, the final derivative of y with respect to w takes a different form.